Hello everyone, I'm Fei Cheng from Imperial College London. Today I will discuss some of our work on low inertia systems. In particular, I will focus on the discussion around the reason why we believe it's critical to link the low inertia, low short circuit current capability with the system scheduling, and also how it can be linked together in an efficient way. So to start with, as we all know that the global decarbonization will be largely achieved by renewable energy resources. However, from system operation perspective, those resources have their own characteristics that we have to consider. To start with, most of the resources like wind PV are intermittent. Their output are variable. We have very limited control about it, apart from occasionally curtailing them, which is anyway very expensive. To make things worse, those resource variabilities cannot be predicted in high confidence. So that will increase significant uncertainty in the system operation. In the past 10, 15 years, significant research has been focused on these two elements, a series of new products and also new scheduling methods, also new technologies has been proposed to mitigate these two challenges. Well, as we are going deeper and deeper, penetration of renewables, the other kind of maybe mainly connection-driven characteristics has been put into the light. To start with is the synchronization. Most of renewables are connected from power electronics, which means they are electronically decoupled from the grids. When the event happened in the system, they will not act as conventional generators by providing either inertia or primary response. Which will have significant impact or challenge in maintaining the balance in a second-by-second basis. While at the same time, the converters have another physical limits regarding their short-term rating. They can barely overcurrent at even very short periods, which quite different from conventional generators. This may have significant impact on the system protection element. So today I will start with discussing about the impact of low inertia, then move a bit on the short circuit current, our recent work on that. So for low inertia, the key impact of low inertia, or the kind of most of research focus on, is the how that impact the system frequency evolution. Here is just a demonstration to say, well, when we schedule enough primary response to meet steady state, that's normally we do in the scheduling where we only consider steady state. In the past, in the conventional in the past cases where we have conventional dominant system, because of high inertia, the Rokov and the nadir will automatically meet the requirement. However, for the same amount of primary response, when we have declines in inertia, as you can see here, we will have much faster decline of Rokov and lower frequency nadir, which may violate the system limit and cause cascading failures. So then the question is, can we tackle this challenge of violation of frequency limit? The short answer is yes. Even based on the existing technologies, we can either bring more conventional generator online to provide inertia, or by procure more frequent response, or at last to reduce the largest frequency loss. All of this will be able to make it even without new technologies. However, the question is how we can choose those options. What is the optimal portfolio by bringing more different options? Another deeper question probably we have to answer is basically, that's really how much it will cost to mitigate this challenge if we use these existing technologies, right? If, I mean, we all understand it's challenging, but if it can be very kind of mitigated with very low cost, then that's probably not something we would concern too much about. But on the other hand, if it's bring a lot of costs up to mitigate this, we may need a new technology, right? So to answer these questions, we have to really link the system scheduling with the low inertia phenomena, because the system scheduling element is really reflect the costs element in the system. So that's really why we are focusing on this work in the past 5-6 years. try to basically optimize the system operation while try to maintain the frequency stability in the low inertia system. To achieve this, as mentioned, we have to bring frequency stability, the transient element, into the economic optimization. This is basically bridge to separate, in the past, separate research areas. One is the stability analysis, one is economic optimization. However, I mean, it sounds kind of straightforward. However, it's really challenging. It's mainly if we look at when we do frequency stability analysis, normally, I mean, even in the simplest form, we have to look at differential equations, right? However, for economic optimization, for most of optimization problem, we can only handle the algebraic equations. So how really these two can be linked together? That's bring the tasks for us to solve. So our strategy is on one hand is basically try to simplify the frequency stability analysis formulations, try to develop algebraic constraints if possible, and incorporate that into scheduling, while at the same time to expand the modeling capability of system scheduling program so that we can really accommodate the new need to encoding frequency stability into the system scheduling. So just give the first example is basically how we can really model the frequency dynamics in a simple form. As it is shown here, the frequency evolution in model in MATLAB, which can be described in the simple form by differential equations, first order, where we have inertia, damping, primary response, provision, and the largest loss. If we look at the whole evolution of the frequency, it's really complicated. And there's no clear ways that we can directly link this kind of 20 seconds phenomena into half-hour kind of scheduling steady-state scheduling program. However, as I mentioned, in fact, we do not really care the whole evolution. What we really care is these three characteristics index, which are the Rokov when the fault happens, the nadir, the lowest frequency, and the steady-state frequency. So as long as we can maintain these three frequency indexes, then the system can be operated safely. Although because of the kind of underlying physics law in it, as long as we limit these three indexes, we get the whole evolution as we wanted. So as I mentioned the basic idea, so we did try to solve this differential equation in these three characteristic points, and we managed luckily to have the constraint in each of these points by kind of managing a little bit techniques. We actually managed to have them all in mixed integer formulation, which is readily to be incorporated into system scheduling. The details of the kind of derivation you can find from our 2016 paper. I'm not going to discuss that further. So once we have this scheduling system ability and link that, we applied that as a kind of operational simulator to see how the inertia problem would impact our system. As we can see here, if we are looking at, we simulate three systems, we just discussed two. One is 2015 GB system, which in general, the cost of maintaining a frequency limit is about 200 milli, which more or less the same as the current market form in the GB. And we also look at the 2030 high renewable cases. Just the same costs actually increased to 1.5 billion, which account almost 20% of the overall electricity cost. So this is really first indicator to us that how expensive it is to manage the system nadir, the low inertia system in a business as usual case. So that's also sheds light that we really need to concern this problem to make the system ready when we approaching that high level of renewables. So yeah, the response of that is to kind of naturally to say whether we have new technologies that might be more cost effective to manage the low inertia than the existing three that I discussed. In fact, yes, there are actually a lot of research has been done. For example, the frequency grid-friendly renewables by using wind turbine or deloaded PV to provide inertia or even primary response. There are works on storage, fast injection powers to support the low inertia system, or look at network technologies. like actually DC to support both sides of the frequency evolution. Last but not least, the demand response, which can instantaneously disconnect from the grids to support events. The technologies are all there. There are significant development in the past few years, but not all of them has been, or even we can see not many of them has been really commercialized. The key reason on that is basically because of lack of understanding about their value. To have their value, we have to be able to know how to assess the value of these different technologies. And also from system operator perspective is once these technologies that become available, how we can incorporate them into system operation, right? So to resolve these questions, we did quite a lot of work and try to model different characteristics of each of this option, and also bring that into the system scheduling tool, which there is a level play field to these technologies to compete and to understand their different values, and also ultimately to know what is the right portfolio of technology to enable future low inertia system in a cost-effective way. I'm not going to go details, but please feel free to refer any of these papers. I'm happy to discuss further if you're interested. So I just gave a very quick example because of time limitation is battery storage as example. Of course, you can see them the same as conventional generators, provide primary response, but in that case, they will never make into the market because of our own cost. However, the battery storage can do much better than conventional generator by provide faster services, which has in fact been recognized by ERCOT and also EGB operator by introducing new services. So as shown here, in these two systems, we already have to distinguish primary service with different kind of speed because of existing of battery storages. However, this will bring a challenges how really we can optimize these two services. As now the primary response, if you look at it in the aggregated way, there will be a turning point where once the EFR has been delivered, how can we incorporate that into the system scheduling. Actually, we did that follow the same philosophy we have. We expand the swing equation to consider this the turning point of the total primary response delivery. And we did manage to get the constraints. The roll off and the steady state are very similar as the previous constraints I have mentioned. But however, the nadir constraint looks much more complex now. We now have the inertia EFR, fast response, slow response, loading, deloading of large loss as decision variables. You can see that this have a multiplication of the decision variables. We also have squares. So it's a very highly nonlinear problem. And you can try to linearize, but you can never done that efficiently. However, if you have a closer look and also redefine some of the decision variables, it's actually turned out to be a rotated second order constraint here. By reforming it, we can actually put that as conic programming problem, and this can be efficiently solved. This is the basic second part I have mentioned. We have to expand also the UC modeling capabilities to accommodate the need of taking into consideration of stability limits. In this case, we expanded the traditional UC based on mixed integer formulation to the frequency constrained UC, which is a mixed integer SOCP, which can be effectively optimized. Due to time, and then a follow-up work is we fully expand this two service only to any service that you want to provide, and that's we can accommodate and optimize the portfolio if you're interested in refer the paper. Okay, another thing, because of time, I just quickly going through. After the low inertia challenge, well, we have kind of gradually clear a picture of how to mitigate it. Another thing, maybe more harder, more physical limits for the converter is their limited overloading capability. Compared with conventional generators, which can provide up to 6.5 short-term overcurrent. The power electronics, most of only maybe 1.2, and then as shown here, the overall short current will be reduced in the future, and this may lead to the protection problems and also long onset voltage oscillations. So then the question is similar as inertia phenomena. Can we incorporate the short circuit current into the scheduling problem, where the outcome of the scheduling can maintain the short circuit current, and then we can understand to what extent it is a problem and what is the cost to mitigate it. Yeah, we did a bit short circuit analysis with IBGs, where this very traditional analysis where we assume synchronous generators modeling and IBG modeling, where IBGs are considered as constant current source. This is a bit over optimistic, but this is the best they can do. So in reality, they may actually provide a bit lower than that because they are voltage dependent current source. And by using the classic superposition method, we can actually calculate the frequency current, the current limit in each of the nodes, and limit that. However, you can see here we really need the impedance, the equivalent impedance of the grid at each node here. This is straightforward. If we are, let me give an example. If we are looking at the after UC problem, we do short circuit analysis when we know all the generation status. It's quite straightforward to calculate the equivalent impedance. However, if we are incorporating that into UC for the grid admittance, for the generator admittance, there will be decision variables, whether the generator online and how much the converter is online. Those are decision variables, and then there will be a kind of inverse. If we calculate the impedance, equivalent impedance of the grids, there will be a inverse with decision variables, which cannot be really solved in the optimization problem. And then I'm not going to go till then we think about two methods. One is the analytical, where we formulate the whole thing as constraints instead of doing inversing, and then combined with a with the microscale relaxation, we managed to have the exact formulation, which is very accurate but cost inefficient because we need n square additional variables and 4n square of constraints to optimize that. Details you can see that in the paper. And then we also borrowed a bit more data-driven methods where we fit a curve that can describe the short circuit current as a combination of decision variables of conventional generator and also online inverters. And we have three different regressions. You can put that in the paper, and the one that borrowed back classification problem work best. And then we have demonstrated that if we don't have short circuit current, we do have some problems that some of the nodes cannot provide enough short circuit current. Once the current is implemented, we can have that all meet the 5 PU requirement, which validates the constraints. However, to maintain the constraint, we can see the significant operating cost increase because this is a relatively small test case. It's kind of a bit too exaggerated, but it demonstrates that the challenge is there. So then similarly, when we see the challenges, we want to look at solutions. Here we investigate two options. One is the power electronic capacity, whether if we can increase the overloading capability, or we can reduce the need of kind of short circuit current to trigger protection. And we can demonstrate, kind of quantify the value, and then understand what would be the best option, or what is the best co-evolution of these two options in the future. The details you can all see that in the new paper that we published. Sorry, a bit over time. I think that's all I would like to say. So today is basically I would like to really emphasize the importance of link all these particular challenges into system scheduling in order to understand to what extent this is a real problem and what is the kind of best combination of the options in terms of cost effectiveness to make these challenges. I think that's all from me. Thank you very much. Please do keep in touch if you have any interesting. Thank you.